Now let's start with the linear interpolation, in which we only use the first finite divided difference. So we truncate after that the terms of the Newton polynomial, and eventually we will have only actually this data, this function. So fx0, define first finite divided difference, and difference of the input on data that we have that we want to find the output, minus the zeroth or the first data point of input, which shows that in the linear interpolation actually we will have 2 points, x0 and x1, and the function values of them. So in a graph you can see x0 and the function value, and x1 and the function value. So maybe the curve is like this, but because we are fitting a linear interpolation, it has to pass through these points, and it's a linear actually function. You can see here the demonstration of is this, and we can also show that this can be obtained through the similar triangles over here. So x is the point that we want to find the unknown data point on the function. Maybe it's over here. So we will just draw a line here between 2 points, and also for x we will cut this line over here. So we will have a triangle similarity. You can see here this edge divided by this one, or actually this edge divided by this one, is equivalent to this edge divided by this one. The ratios are the same for the similar triangles. So when we write them, you can see fx1 minus fx0, this part, and x minus x0 is here. Then fx1 minus fx0 here, and x1 minus x0 here. And if we isolate f1x, because we don't know this value, we need to isolate this, we will obtain the linear interpolation, which is the same as the Newton's first order polynomial actually. And this gives the slope of the line which connects the points, and finite divided difference approximation of the first derivative. So slope means the derivative anyway. Over here, for instance, the derivative is here, but here it is estimated with this one. And in general, the smaller the interval between the data points, the better the approximation. So when we have this x1, for instance, over here, we will have a better approximation linearly. So and the reason is that as the interval decreases, a function will be better approximated by a straight line. So when we have maybe multiple linear interpolations, also to be able to predict this with linear interpolation in a more accurate way. Here we have an example 15.1 for linear interpolation, and we will estimate the function value when we use natural algorithm for the input of 2 using linear interpolation. And we will have, for linear interpolation, we need 2 data, and for this data we use the function of ln, or the natural algorithm, for input of 1, which is 0, and also input of 6, which is 1.79. So we have these data. 1 for x equals 1, fx is 0, and for x equals 6, fx is 1.79. And in here, then we will repeat the procedure but use a smaller interval. So we will use, instead of 6, we will use 4, which has a function value of 1.38, and again we will find the ln value of 2 as from the interpolation. On the right hand side you can see the function. Actually this is ln function, and for 1 it is 0, for 6 it is around 1.8, and for 4 here 1.38 over here. But of course we don't know the function behavior, so we will interpolate it using linear interpolation. The first one is this, from 0 to 6, and we can write 6 here and show this way. Basically this is 1.79, 1759, and for 4 this is 4, somewhere here 1.386294. So let's use ln 6 value first. So we will have this function, or this linear interpolation in between, and our estimation for 2, we want to find the value of 2, which is actually over here somewhere, but we are estimating with this You can see somewhere here. Let's calculate it using the linear interpolation formulation. So this is our linear interpolation formulation with the Newton's polynomial. And we know that x1 is 6, x0 is 0, and fx1 is 1.791759, and fx0 is 0 actually. So let's write it down here. For x1 is 6 and x0 is 0 and x1 is 6. f1, 2, we want to find 2. fx0 is 0, so 0 plus 1.791759 minus 0 divided by 6 minus 0, and 2 minus 0. This is 2. We want to find the value for 2. That's why it's 2. And here we find f1x equals to 0.35 83153. And if we calculate the true error, simply it is the actual value is, it says here the actual value is 0.69. maybe we can write here the actual value here, 0.6931472, and you can see we calculate it as 0.3583519. You can see it's almost half of it, so it's about like 50%, but let's calculate it. 0.6931472 minus 0.3583519 divided by 0.6931472 times 100, which gives us an error of 48.3. So it's a pretty large error actually. What if we use a smaller value for the, instead of 6 we will use 4 as the data point, which gives us this. So we will have a better approximation of the true function, you can see, because we narrowed down the range. So interpolation means the data will be in between the range of the data. If we are using 1 and 6, we can predict data between 1 and 6. If you are trying to predict something outside, it will be extrapolation. This is not the topic, and it may not provide a good value for it. So let's use x1 0, x0 0, x1 4. For this f0 is 0. For this f4 is 1.386294. Then let's calculate f2. Again, use the formulation here. fx0 is 0 plus fx1 is 1.386294 minus fx0 is 0, 4 minus 0 times 2 minus 0. And from here, f2 is equivalent to 0.462091. You can see that we are getting closer to the actual value, which is here. And if we calculate the error using this, you can calculate this. I'm not going to write it down, but you can simply write this here and the true value here, divide by the true value, and the result is 33.3%. You can see that the error decreased. Of course, it is not very well. So the closer to the point, for example, if we get data from here, we will able to predict in a better way. The closer to the point, the better accuracy we obtain. So this is important for this interpolation scheme, let's say. And by narrowing down the range, you can obtain better results.